So, now what we will see is we will look into the Numerov algorithm. So, the Numerov algorithm is typically used to solve second order differential functions of this form psi double prime x equals to f x psi x plus s x. So, this is my a general second order differential equation form, which is typically used by solving the Numerov algorithm. Now, since we are trying to solve a second order differential equation, so what we will be needing is two boundary conditions. So, let us put the two boundary conditions. Let us assume that or we will be needing two initial conditions. Sorry. So, my initial conditions are, so first of all psi at x 0 is equal to psi 0 and the first derivative of psi at x 0 is equal to psi prime 0. So, this is what we are we want to solve, and we want to solve it for a complete range of x. So, what we need to do is we need to discretize x in using a uniform grid. So, the next step will be to discretize x, and in this case we will be using a uniform grid. So, what I can do is, what it means is basically x at a point k at the kth point of my grid. So, suppose this is my integration range, say from a to b. So, what I do is I divide it into certain number of grids. So, this is my 0, this is 1, 2, 3, 4, this is k, and then it goes on so on and so forth. So, now x at k is given by my k delta x, where delta x is the width of this particular grid. Okay. So, in many physics problem and also in this type of mathematical problem. So, what we use this type of trying to convert a mathematical problem to a numerical one, what we often use is the Taylor series expansion of my function, and this is precisely what we are going to use again here. So, what we do is we do Taylor series expansion of psi x at x plus delta x and x minus delta x. So, my psi x plus, so that is say at k plus 1. Okay, let me just write it a bit more carefully. So, basically what I am doing is, the idea is this is my k, this is my k minus 1 and this is my k plus 1. So, I know the wave function here as psi k, and this is psi k plus 1 and this is psi k minus 1. So, what I am going to do is I am going to write psi k plus 1 as psi x k plus delta x and psi k minus 1 as psi x k minus delta x. And this stuff here, this I will do a Taylor series expansion about x k. So, what I will get is the following thing. So, my psi at x k plus 1, this is nothing but psi at x k plus delta x, which is equal to psi k. Okay, this notation I will come to later, this short form, let me write it in the full form first, psi at x k plus this following series expansion n equals to 1 to infinity delta x to the power n by n factorial psi n x k x k. This is my, say I call this as equation 1. So, just note one thing, that when I write in this fashion, this means the nth derivative and not psi to the power n. Okay. So, that I mean I just wanted to make it clear, so that there is no confusion later. In the similar way, what we can do is we can write psi at x k minus 1, that is psi at x k minus delta x. This will be same except with slight changes. So, the first term is psi x k, and then we have under summation n equals to 1 to infinity. Now, the additional term which we have is minus 1 to the power n, and then the rest are again same, delta x to the power n by n factorial psi n x k. Okay. This is my equation 2. Now, what I will do is I will add 1 and 2. So, I will add 1 plus 2. So, what I will get is psi x k plus 1 plus psi x k minus 1. This will be equal to, so I will add this term plus this term. So, I will get 2 psi x k, and then if I look into these terms. So, the terms are same, the only difference here is for odd values of n. So, for example, n equals to 1, this term in this second equation, this will be negative, while the same term in the first equation will be positive. So, it will be cancel out. So, what will be left are only the terms. So, this will be true for all the odd values of n. So, when I add up equation 1 and equation 2, the terms will get cancelled, and we will be left only with the terms with even values of n. And so, if I collect them, so what I will get is the following. So, what I will have is the delta x square psi 2 x k. Again remember, here x psi 2 is the second derivative of psi, plus 1 by 12 delta x to the power 4 psi 4 x k plus order delta x to the power 6. So, this I call as equation 3. So, I am neglecting the I am keeping till the fourth order term, and I am neglecting the other terms in my expansion. So, the next step what I will do is I will pick this psi x and I will bring it to the left hand side. So, if I do that, what I land up with is psi x k plus 1 minus twice psi x k plus psi x k minus 1. This will be equal to delta x whole square psi second derivative of psi at x k plus 1 by 12 delta x to the power 4 fourth derivative of psi at x k plus some order delta x to the power 6 terms. Okay. So, this is what I get, and if you look at the expression in the left hand side, this part here. So, this reminds me of one thing. So, this part is nothing but my delta 2 psi of x k, right. This is the central difference formula which we always use. So, using this, so what we can do is we can rewrite this equation in the following way. So, what we have is on the left hand side of this of the equation in the previous slide. So, what instead of having that 3 terms, we write it as psi x k, this equals to delta x square psi 2 x k plus 1 by 12 delta x to the power 4 psi 4 x k plus order delta x to the power 6. Now, if you look at these expressions, so what is unknown here is this thing, this term we do not know, we do not know what is the fourth derivative of my wave function. Okay. So, to evaluate it, what we will do is we will again use the trick of the central difference. So, what we will do is we will write this fourth derivative of x k as central difference of second derivative of x k. Okay. So, and once we so how do we do that? So, we do it in the following way, again we use the help of Taylor expansion. So, we write psi 2 x k at delta x plus delta x k, that is k plus 1, this we write as psi 2 x k plus delta x psi 3 at x k plus delta x square by 2 psi 4 at x k plus other higher order terms, and similarly we write psi 2 at x k minus delta x, that is at k minus 1th point of my grid as psi 2 x k. Now, the first term will be again a negative one, delta x psi 3 x k plus delta x by sorry, it will not be whole square. So, delta x square by 2 psi 4 x k. Now, if we add these two terms, so if we add these two equations, so what we will get is psi 2 x k plus delta x plus psi 2 x k minus delta x, this equals to twice. So, we have one here and one here, twice psi 2 x k, these two terms cancels out if I add them, plus, and here I get again twice the same term. So, what I will get is delta x square psi fourth derivative of psi x k plus other higher order terms. So, what we do as before, what we will be doing is next step will be we can bring this term to this side, and what we will have as a result is delta x square psi fourth derivative of psi k x k is given by delta 2 psi 2 x k. Okay. And what we will do next is, once we know this expression, this term, this thing, so this we will plug into this particular equation, and let us see what we get. So, what I can do is I can call this as my equation 4, and this as my equation 3 prime. So, the next step will be, so using 3 prime and 4, what we get is the following thing. So, that is del 2 psi x k, this is equal to del x square psi second derivative of psi at x k plus 1 by 12 delta x square del 2 psi 2 x k plus my order del x to the power 6. Okay. So, this is what I get. and I call this as equation 5. Now, if you go back and so you and just to recollect, we started off with this is my differential equations, right. So, this is the differential equation which I am solving at present. Okay. So, this differential equation gives me the second derivative of psi x. So, we will use the fact here. So, coming back to here, what we have is, as per the differential equation, my second derivative of x is given by f x psi x plus s x. Okay. But now we bring in our Schrodinger equation. Our Schrodinger equation, what we have is minus h cut square by twice m d 2 psi d x 2 plus v x psi x equals to e psi x. So, once we and if we do some simplification, what we will land up is minus twice m by h cut square e minus v x psi x. So, now if we compare this equation, this one and this one, so what we find is that my s x equals to 0 in case of the Schrodinger equation. So, for the rest part of the derivation of the numerical algorithm, what we will do is that we will basically we will be looking for solution of this form, where my psi the second derivative of psi x is equal to f x psi x. Okay. So, this is the solution we are looking for. This is the differential equation which we are trying to solve, and then we will use it here at this particular point. So, what we get is the following equation: del 2 psi at x k equals to grad del x square f at x k psi x k plus 1 by 12 del x square del 2 f at x k psi at x k plus order del x to the power 6. So, what I have done is basically here, instead of so this psi 2 here, I have that is the second derivative of the psi. I have plugged in this value f x and psi x, which I get from the differential equation, which is my original differential equation. So, once I do that, then what we get is the following. So, now psi k plus 1 minus twice psi k plus psi k minus 1, this is equal to now del x square f k. So, I am now what I am doing is I am now getting rid, to make it simple, I am now getting rid of this dependence or the functional dependence on x k, and I am just, so when I write f as a suffix k, it means f is a function of x k at the kth point of my grid, and then psi k plus 1 by 12 grad x square. So, here for this part, that is this one. So, for this part, what I will do now is I will use the second central difference formula for the second derivative. So, this I am writing in this form, that is f of k plus 1 psi k plus 1 minus twice f of k psi k plus f of k minus 1 psi k minus 1. Then I have this term also, the order delta x to the power 6. So, just to write what I have done is I have replaced in this equation x k as k, x k plus 1 as k plus 1 and x k minus 1 as k minus 1. So, this is what I did here. I have just shortened the summation. Now, let us try to simplify this still further. So, let us define another variable which is phi k as the product of psi k into 1 minus del x square f k by 12. So, if I do that, what now this whole equation, this particular equation, the equation which I am marking with this green line. So, this equation, I will rewrite this equation in terms of phi k. So, what I will have is, if I am not doing the detailed algebra, I am just writing the final result. So, what I will have is phi k plus 1 equals to twice phi k minus phi k minus 1 plus del x square f k psi k plus order del x to the power 6. So, using this, where in this we can get psi k equals to phi k into 1 minus grad x square f k by 12 to the power minus 1, and similarly where psi k plus 1, what I have done is I have replaced it by phi k plus 1 minus grad x square f k plus 1 by 12 to the power minus 1. So, this is my equation. So, what this equation tells me is that if I know the value of phi k, if phi k and phi k minus 1 if known, then we can find phi k plus 1, and once we know phi k plus 1, then by putting it in this equation, in this one, we can find psi k plus 1 also. So, this method, it's a very elegant method, and it is also much more elegant than the Runge-Kuttan method, which you which you have learned about earlier. So, once we get this, so what is also unknown is our E is also unknown, if you remember, as I was talking earlier. So, not only the wave function is unknown in this equation, the E is also unknown, and this is involved through the f k function. So, this is my f k function, just for your reminder. So, this is the f k function. So, the E enters to the equations through this particular f k function. So, now we will, this is how the Numerov algorithm is derived, and basically, since it is a second order differential equation, as you can see from the equation itself, it depends on two starting initial conditions. So, we need to know phi k and we need to know phi k minus 1. These are the two things we need to know to find out the equation at the next value of the wave function phi, or in terms of wave function, we need to know psi k and psi k minus 1. So, this one and this and similarly psi k minus 1 also, and then we can, from there we can find psi k plus 1.